Hey, what's up? It's me again, your old friend, and welcome back to another coding interview question. While I was away, well, not really away because I did make one video, it's not about algorithms though, we got to 100 subs. Insane! I mean, when I started this channel, I never ever expected 100 people to be interested in me talking about algorithms and data structures. So thank you so much to everyone who's been supporting the channel, everyone who's part of the journey. If you ever liked a video, subscribed, left a comment, I really appreciate you, and I look forward to the next 100 subs. So let's solve this question. This is a really interesting question, because it's almost impossible to solve without doing some charts and graphs, and it's actually one of my favorite interview questions because it gives you the opportunity to demonstrate your vision, and that could really spice up the interview process. The question is called Trapping Rainwater, and let's see how to solve it. So given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it is able to trap after raining. Now, this prompt looks really intimidating, so don't sweat it. Let's draw a chart. So you're given something like this, right? All you're given is an array, like this one right here, representing heights of a bar. And those bars all have the same width. So this bar has a height of 1. You can see it right here. The other one has a height of 2, 2, and 2, and 0, and 0, and like that. So say for example, it rains. I don't know what the color of rain is, so I'm just going to do purple. Maybe I do know what the color of rain is. It's kind of transparent, but there's no transparent color. Anyway, so say for example, it rains, right? And if it rains, you should determine how much water is trapped between these bars. So how do you do that? First of all, let's determine where the water is going to be trapped. So if it ever rains, water is going to be trapped here, around here, all of here, and all of that. So this question screams dynamic programming at you. For dynamic programming, we're going to look at sub-problems instead of the entire problem. And what I mean by that is, specifically for this question, instead of looking at the total amount of water trapped above all the bars together, we're going to look at the amount of water trapped above each bar. Let's look at that. So for the very first bar of height 1 at index 0, 0 units of water is going to be trapped here, because every water that rains on top of here, I really don't know how to say it, it's going to spill off. Like, it's going to go this way. All right, it's going to spill off, and spill off, and spill off. So nothing's going to be trapped here. Same for a bar of height 2. But when we come to a bar of height 0, there's going to be some water trapped here, around here, right? And that's going to be of height 1. And then when we come to this guy right here, we're of height 1, there's going to be some water trapped here. And then when we come to this guy right here, 0 units of water is going to be trapped here actually, because it's going to spill off over here. And then when we come to a bar of height 2, there's going to be about 1 unit of water trapped here. So all we have to do is, after finding the units of water that's going to be trapped above each bar, we can add them up all together after doing everything and then return the sum. The meat of this algorithm is going to be dependent on how we calculate the individual amounts of water trapped above each bar. Let's take a look at the bar of height 2 at index 0, 1, 2, 3, 4, 5, 5, at index 5. The amount of water trapped here, right here, I'm going to color it in green, is dependent on the highest bar to the left and the highest bar to the right. The highest bar to the left is this one, 3. And the highest bar to the right is this guy, 4. So the total amount of water trapped at 2 is going to be dependent on the highest bar to the left and the highest bar to the right. This really tells you that we have to iterate through the array and find the highest bar to the left and the highest bar to the right in order to determine how many units of water is going to be trapped above each bar. So after finding the highest bar to the left and the highest bar to the right, we're not done yet. What we have to do is we have to find the minimum of those two values. So for 2, highest bar to the left is 3, highest bar to the right is 4. We have to find the minimum of those two values. Minimum is 3. And after finding the minimum, and then we could extrapolate to find the amount of water trapped above 2 to be 3 minus 2. And that is 1. So 1 unit of water is going to be trapped above 2, and that is this guy right here. So how did we determine that 1 unit of water is going to be trapped above 2? Let's write up the formula. Let's say trapped water, TP, is going to be, the minimum of the two maximum values to the left and right. So I'm just going to call it min max value. Min max. Let's just say mx, minus the height of the current bar. So let's say height. Fair enough? But we do have one caveat though. If the height of our current bar is greater than the highest bar to the left, then the minimum of the highest bar to the left and the highest bar to the right, then 0 units of water is going to be trapped above that bar. Let's take a look at an example of the bar with height 3. And that's this guy right here. The highest bar to the right is 4. Fair enough. Highest bar to the right is 2, has a height of 2. Minimum of 4 and 2 is, you guessed it, 2. And then the height of 3 is greater than the height of 2. So if you apply this formula, that's TP, trapped water, above 3, is going to be equal to min-max value, which is 2, minus current height, which is 3, negative 1. So like 0 units of water is going to be trapped above here. That tells you that all the water that rains on top of height of bar 3 is going to be spilled over. So we have to take care of that edge case. It's going to be fairly easy to do as we dive into the code. But for now, let's just go through the entire example and then see what the answer is. Okay. So first of all, what we have to do is find highest bar to the left at every index. So I'm just going to call this left max, lm. For height 1, left max is 0 because it's the very first index. There's no left bar, so 0. For height 2, highest bar to the left is 1. Height 0, highest bar to the left is 2. Height 1, highest bar to the left is 2. Height 3, highest bar to the left is 2. This 2 right here, highest bar to the left is 3. And for 4, highest bar to the left is 3. And then we find highest bar to the right. And let's call this right max. Just gonna say RM. And we start at 4. We start from the back, coming. No, it's gonna be easier to do that way. And 4, highest bar for this guy to the right is 0. And then highest bar to the right of 2 is 4. Highest bar to the right of this 3. Now we're at 3. It's going to be 4. Highest bar to the right of 1. Guessed it. 4. Highest bar to the right of 0. Again, 4. highest bar to the right of 2. I'm quickly just going to go through 4 and 4. And all we have to do now is to calculate total units of water trapped at each index. Bring the formula down. So for index 0, it has a height of 1 and a left max of 0, right max of 4. So the total water trapped, should choose my colors better, just going to say TP, is going to be the minimum of the left max and right max, which is 0, minus the height, which is 1. 0 minus 1, negative 1. Then we know that 0 amounts of water is going to be trapped there, so we just put 0. For this guy, minimum left max and right max is 1. 1 minus 2, negative 1. And then we know it's going to be 0. And then we get to bar of height 0. Minimum of left and right max, 2, minus height 0. So 2 units of water is going to be trapped above here. And then we get to height 1. It's this, and this. Total, minimum of left max and right max is 2. 2 minus 1, 1. And then we get to this guy, 3, 3, and 4. Minimum of both is going to be 2. 2 minus 3, negative 1. Yeah, nothing's going to be stored there. So 0. And then we get to 2. Minimum is 3. 3 minus 2, 1. And then we get to 4. And nothing's going to be on top of here. And then we add everything together. So that should be 2 plus 1 plus 1, and that's 4. So total is going to be 4. I think for this, it's going to be stopped right here. So here's all the water that's going to be trapped. I really, really wish it wasn't this messy. The code's not going to be as messy as the illustration. And as you can see, we're declaring like 3 more arrays to store the left max, the right max, and the total water trapped. We can do all of this in just a single array. And that's the beauty of dynamic programming. So let's dive right into it. So first I'm going to code the solution that's easier to understand, in my opinion. So we need an integer array, and that's going to hold the right maxes. Let's first do for the left maxes. And it's going to hold as many elements as the heights. So height.length, and then we declare another integer array for the right maxes. It's going to hold as many elements as the heights array. And then we have another one for total water trapped. Fair enough. And now we have to loop through the array to get the left maxes. So initialize the first left max to be 0, because when we start, there's not going to be anything to the left, so initialize to 0. And then we do a for loop, I equals 0. I goes all the way to the length of height. I. And then we could set left maxes at I to be the current left max. So left max. And then we calculate the left max for the next iteration. Left max for the next iteration is going to be the maximum value of our current left max, or whatever we have at heights of I. So this means that if our current height is greater than the left max, so for the next iteration, that should be our left max. And that's pretty much it for this for loop. We're going to go through another for loop, really messy. I promise you I'm going to clean it up. Oh, that's for I is less than, or sorry, this is for the right max. I think I should do functions. Oh, I should do comments. Let's say populating the right max array. Now we're going to start iterating from the back, from the very last element. So I is going to be equal to the index of the very last element, height the length minus 1, I is greater than or equal to 0, and then we increment I, and then we have to initialize an initial right max, which is going to be 0. And then we could set right maxes of I, to be equal to our current right max. After that, we have to recalculate the right max for the next iteration. So right max is going to be math.max, maximum value of whatever we currently have at right max, same for the left max, and you guessed it, whatever is in heights of I. So after that, now we have to calculate the minimum value of the left max and the right max. So let's call it in minimum max value. I'm just going to call it min max val is equal to, this time, math.min of right maxes of I and left maxes of I. So now that we have this minimum max value, we can now calculate the total water trapped at this index. So remember, total water trapped is equal to, I think, min max value minus height. So total water trapped, total water at I is going to be equal to min max value minus height of I. But remember, there's going to be cases where we might get negative answers if the heights of I is greater than the minimax value. So we have to take care of that edge case. It's actually quite simple. So if height of I is greater than minimax value, then all we have to do is to set total water at this index. Total water at I would be equal to 0, because no water is going to be trapped there. And then else, what we can do is we can set total water to this right here. And there we have it. So at the end of everything, all we have to do now is to add up all the individual units of water trapped above each bar and then return it. So you could easily do that with stream and arrays. So return arrays.stream. Do I have the arrays library imported? Oh, I don't think so. Import just all of them. We're streaming. What are we streaming? I think total water. Dot sum. And that's it. I'm quickly going to go through, make sure I have my semicolons checked check everything, run code. Oh, this should be I minus minus because we're going back, and then run. Oh, cool, accepted. Now we're gonna clean this up a little bit, as promised, or maybe we should talk about the time and space complexity. If you're really bored at this time and you want to live, you want to dip, you can do that, bro. Time and space complexity is going to be O of n for both of them, and if you want to know why that is, stick around for a few minutes. All right, so we don't need these two. What we can do is we can declare a dynamic programming array, call it height tilt length, and then left max is going to be 0, and then dp of I is going to be left max. Then we calculate left max for the next iteration. I should just call this populating left max. And then we have the right max, height tilt length. Instead of right maxes of I, now we already have right max, so we know that is the case. This should come after we've used this first right max. So here, when we have the right max, we can calculate the min-max value. So min-max value, in this case, is going to be left maxes of I, that's dp now, dp of I, and, you guessed it, right max. So at this point, dp of I only contains the left maxes. So now we have the right max. And now we can check if the height is less than, height's greater than min-max value, then total water is going to be 1, else total water is going to be whatever we calculated. And then after that, we can recalculate the right max for the next iteration. And then let's try to run this. We don't have total water of I, so it should be dp. dp, sorry. And yep, so this can be an if expression, make the code even shorter. So if dp of I is equal to, so height of I is greater than min-max value, then we return 0. Otherwise, we just return min-max val, and then take all this code away, and then run this. Cool. Submit. Yep. And that, my friends, is the beauty of dynamic programming. Let's dive into the time and space complexity of this algorithm. For time complexity, we're iterating through the array in 2 for loops. And those for loops are not within each other. So if you really want to be technical, time complexity is time O of n plus O of n, because we're doing O of n, O of n. But then that's going to be 2 O of n. But in big O notation, we drop constants. So total time complexity is simply going to be O of n. For space complexity, we have a dynamic programming array that stores the total amount of water, the individual amounts of water trapped above each bar, and that's going to be O of n. So that's it for this algorithm. I hope you find this video informative. Like I said, I really like this question because it is very intuitive, and I finally solved a hard question. Yay! So share it around the community, like and subscribe if you like more content like this, and comment down below. Let me know if there are ways we could have make this algorithm work better, and I'll see you in the next video. Bye!